Today, we shall discuss something about rotational motion. Start with, let us just recollect a few things of our art. Let us recollect the linear motion. For linear motion, we have seen that chapter we have seen that if there is a point object, always considered a point object for the comfort mathematics or arithmetic. And if there is a force, then by Newton's law of motion, the body starts moving in the direction with, say, an acceleration A. Acceleration is there as long as the force is there. There are three things we have seen. Acceleration is there as long as the force is there. And number two, we have seen that acceleration is in the direction of the force. Acceleration is and also one more thing that we have observed, the measurement of this force is equal to mass of the body multiplied by acceleration. This was the linear motion. Chapter we considered a circular motion. In circular motion, chapter, we have seen that if there is a body which moves in a circle, the center say O, and same point body, it moves around a circle. Then also we have seen, we have studied this feature where we have seen that if the body moves in circle, then there is a angular velocity omega and there is an angular acceleration alpha. And also we have seen that this body will have a tangential velocity v, and if this radius is r, then we have seen some relations about this. Here we have seen some relations like, if we want to put the relations in linear motion, in linear motion, and say this is circular motion, have seen the relations in linear motion, the displacement S, where a circular displacement is designated by the angle theta. And I remind you, theta is always expressed in radian. Now, in linear motion, acceleration is designated by A. In circular, acceleration is designated by alpha. Second square. Displacement is meter and acceleration is meter by Similarly, in linear motion, velocity is designated by v, which comes of meter per second. In circular motion, velocity is expressed by the word by the letter omega, which is radian per second. In linear motion, there is a formula force is equal to mass in action. And there are many other formulas that we have learned here. In linear motion, there are equations of v is equal u is the initial velocity plus a t, s equal to ut plus half a t square, and v square is equal to u square plus 2as. There are analogous equations in circular motion where v is replaced by omega. Omega is equal to omega 0. Here, omega 0 or omega naught is the initial angular velocity plus angular acceleration alpha into time. Similarly, total angular displacement theta is equal to omega 0 t plus half alpha t square. And also omega square, that is final angular velocity omega square, is equal to initial angular velocity omega naught square plus 2 into theta, 2 alpha into theta, 2 alpha into theta. We have already seen. Also, please recollect that tangential velocity v, tangential velocity v is equal to r into omega. The circle into angular velocity. Also, tangential acceleration alpha is equal to tangential acceleration, not alpha. Tangential acceleration is a. Tangential acceleration a is equal to r alpha. These are the primary equations. And in linear motion, there was a formula for measurement of the force F equal to ma, and an analogous formula we have not yet seen in angular motion or circular motion. Now we rotational motion. Motion. Rotational motion is very much like circular motion, but with a little bit, very little bit of difference. Circular motion, we have considered a point object which is moving in a circle. Rotational motion, we normally consider a extended object, like say this is an extended object, which has, of course, a thickness, but for at the beginning of this chapter, we shall consider the thickness is very negligible, but everything has a thickness. Now, this body, this lamina or the piece of metal or whatever it is, let us say there is a small hole here, and this body can move around this axis. This body can move around this axis. So this is A, this is O, and this. Take a small sheet of metal and make a hole and put a nail through it. And if you knock this body, it will start rotating. This is rotational motion. The formulas, etc., are very much like circular motion, except a small difference here. Suppose if you knock here, suppose here, if you apply a force, if you some force, then obviously it will start rotating. Now the whole body is rotating. The whole body has got angular velocity, whole body has got angular acceleration, etc., etc. But the values of those angular acceleration or angular velocities, of course, different from one point, say from this point to this point to this point, is it different? It is just like the circular motion where there was one point. There are combination of so many points, one here, one here, one here. So conceptually, it should not make many much of a difference. Only it is the combination of many such points. If it starts rotating, then the whole body will start rotating, and drawing the picture may be a little difficult, but still I'll try. If it starts rotating, then at some point of time, then this body will take a position like this. That means the body has rotated. To measure the angular velocity, etc., of course, you have to refer to only one point. Let us consider this point. Let us consider this point P. And let's say this point P has come here. Let's say this point is P has come down here. So here, this is the motion, path of the motion of the point P. And point P has got an angular velocity omega, and the radius of the motion of the point P is once again r. It will have angular acceleration, etc., everything. And its total angular movement from here to here, it is measured by or designated by the angle of movement of theta. Now, in the rotational motion, mind it, in the rotational motion, we have not yet measured the seen that this force F is responsible for the rotation. The after effect with its after effect. The after effect is angular velocity, after effect is angular acceleration. But what is the effect between this force and this angular acceleration? We have not yet seen. In the rotational motion, let us investigate a little bit more into this rotational motion. In rotational motion, a new terminology comes which is called torque. Torque. Normally, it is designated by lowercase small tau, And in some textbooks, it is also designated by capital gamma. Both acceptable. Know all the symbols because you will appear not only in your school examinations, you will also appear for your board examinations and everything. So that different people use different symbols. Now, what is torque? Now, torque is, let us statement that torque is effect of the force acceleration. Torque is F in rotation is a literary term. In mathematical term, it is the angular acceleration. The acceleration. The torque, measurement of torque is done this way. Once again, same lamina, let's say it is the same lamina. I make a little bigger picture so that it is easy to understand. And you have made a hole here, and you have, suppose you have put a nail here, so that nail A, O, B. So that if force is applied, this lamina can move clockwise or anti-clockwise. Now let us say there is a point P, the point P, and you apply a force, say, in this direction. It could be in, say, you apply in this direction, right? If you apply a force, obviously, by our common sense, we see that the body will start rotate in clockwise direction. In that case, this is the distance vector, or which also we call position vector, R. This is a force vector, F. Then torque is measured by the vector cross product of position vector cross product vector and the force vector. What is the vector cross product? You should recollect your lessons from the vector algebra, and you will now remember that this vector cross product is the magnitude of R multiplied by magnitude of force into n theta, the angle between them. Now, what is this angle? Let us also try to find out. What is this angle? This angle is this angle theta. Remember, the angle between the vector R and vector F, but by vector algebra rule, theta is always the smaller angle between the two vectors. So torque is Rf sin theta, or vector product of R and F. I don't know whether you still remember, this torque is also a vector, and the cross product is also always a vector. Let me write torque is of this vector, of this torque vector. If you remember from your vector algebra lesson, cross product, cross product, the direction of the cross product is always in the perpendicular direction of the component vectors. That means if the component vectors are in x-axis and y-axis, then the direction of the cross product is in z-axis, either in plus z direction or in minus z direction. Similarly, if the two vectors that you are multiplying are in z-axis and y-axis, of the cross product will be in the x-axis. Revise a little bit of your vector cross product lesson so that you can recollect it for the purpose of solving numerical problems. And there is another easier way of doing it. Let us say, uh, let us say this is the, let's say this is the R vector, and let us say this is the F vector. Then there is a way of determining the direction of this cross product, for which I have to draw a picture, but I'm really not good at drawing a picture. What you have to do, you have to hold your palm, say this is your one finger, this is your another finger, another finger, another finger, and this is your, and in that case, your thumb goes like this, and you have to hold your palm like this. I'm not really good at drawing pictures. You hold your palm like this so that your fingers are pointed towards the R vector. Right? Now, if you close your fingers, then what will happen? Your fingers will come in this direction. Your fingers will come in this direction, and your fingers will then, fingertips will be then on the F vector. In that case, the direction of your thumb is the direction of the cross product. That is R cross product F. If this is the direction of R and this is the direction of F, then this is product. Right? And one thing more, remember, it should be very obvious. Uh, the F vector and the R vector, and then you try to put your fingers, you will find the direction is in this direction, the direction of the cross product. So, in cross product, magnitude of the cross product, that is RF sine theta, remains same in both cases, but the cross product, direction of the cross product RF, let me write it this way, direction of R cross F not equal to the same direction of F cross R. The direction is ulta, opposite direction. Now, normally the at school level children, they have confusion that always seen that the direction of the vector when you multiply it, they're in the same plane. We have seen direction if the vectors are if the vectors they are scalar products or dot products, they're in the same plane. But the cross product direction is in a totally different direction. Why it happens so? Because that is how the vector algebra has been developed. And actual ramification of this, then why it is so, it will be clear to you when you go a little bit forward in your physics lessons, like when you go for electricity or magnetism, you will find this is the correct way of discussing it, right? Then we go to the point. So we have understood what is torque. Torque is the cross product of position vector and force vector. Now let us see the significance of torque. That is most important. Significance of tell you, whenever you are in physics chapter or physics subject, you must always ask yourself what is the significance of it? What is the real life significance of it? Otherwise, you will never get the real pleasure of physics. Now, let us find what is the significance of this talk, right? Now, this diagram, I have shown the actual mathematical diagrams, but in your day to day normal life or normal your numerical sums for your school examinations, etc., you will find it different. You will find it as much a simplifier version. You will find a normally what you will find is a simplified version. Say this is the lamina and this is the axis and this is the force applied. You will find this position vector R and force vector F there. They are perpendicular to each other, then their cross product R into F is equal to 90 is equal to R. That means for your day-to-day numerical problems in your school, you will find torque is actually just a multiplication of the distance of the force applied from the axis of rotation multiplied by the force. As simple as that. So in that case, the simplified version with torque is equal to distance. Distance from where to where? Distance from the axis of rotation to the force. Distance multiplied by force. Shows that if is more, then torque is more. Also, distance is more. This is a simplified version of our earlier statements. That in this case, when the force is applied perpendicular to the distance vector, then if force is more, torque is more. If distance is more, torque is more. Now let us see, does this conclusion really uh, fall in line with our day-to-day experience? Let us see. I'll give you a I'll give you a case. Let us say this is some steel or iron body, and let us say there is a bolt. And this practical life lesson all of you have. Let us say there is a bolt. Now, what you are doing, you are trying to loosen the bolt. You are trying to loosen the bolt. What you will do? You will take a wrench like this, like this, the handle of the wrench. This is the handle of the wrench. And you will hold the end of the wrench and try to apply a force. From your real life experience, you can say the more force you apply, it is easier to loosen the bolt. Right? That means more rotational effort comes into effect. And instead of applying a force here, if you apply put your hand here and try to rotate, then you will see the rotational effect is less. So we see when distance is more, that means when the distance of the force is more, the after effect of applying the force in producing the rotation is more. And other thing is also is very obvious. If we apply more force, then the effect of rotation is more. So this equation tallies with our real life experience. So we have learned what is torque. We have learned what is torque. We shall investigate a little bit more into this torque. We have investigated a little bit more into this issue of torque. Shall go to the next part. Right? We shall go to the next part. We shall investigate a little. Let us draw a line here because we are going to the next part. Oh, what I am really looking for is of linear motion, is of motion, and F equal to ma measures amount of force. Now, is there a similar relation? Is there similar relation certain in rotation? that we are trying to investigate. Once again, let us take a laminar object like this. Which is very thin, and let us consider, yes, the axis of rotation O. There is a small hole in the lamina, and there is a wear or a nail, and this lamina can rotate in this direction or in this direction around this axis of rotation. Now, let us consider any point P. Let us consider any point P. Let us consider any point. A small elemental point P on this lamina, and it rotates. If a force is applied, if it rotates, this point P will start rotating in a circle like this. Right? Starts rotating in a circle like this, then it will have a tangential velocity v. This we have seen from our lesson of circular motion. It will also have a tangential acceleration a. This tangential acceleration and tangential velocity both are linear. Also, also this will have a angular velocity omega and angular acceleration alpha. This angular velocity and angular acceleration is along the arc. Here, angular velocity omega and alpha is along the arc. And let us consider this is the distance of the point from the axis of rotation is r. Right? Now, here, this tangential linear velocity, I write everything for you, this, so that the reference, it will be easier to tangential linear velocity is equal to v, and tangential linear acceleration is equal to a, and we know the tangential force is equal to mass into acceleration, that is mass into acceleration. This force, this tangential force which is working on it, is mass into acceleration. Now, this acceleration A is equal to, we know, is A is equal to R into alpha. This also we know. Now, that there is a centripetal force. There is a centripetal force in this direction. And there is a tangential force in this direction. This centripetal force, that means there are two forces on this body. There are Yes, on this are centripetal force, centripetal force, and find it. Tangential force is there if there is a tangential acceleration producing a circular acceleration. But if this tangential force is not there, then the tangential velocity is uniform, so circular velocity is also uniform. But for a circular motion, the centripetal force is a must. Without the centripetal force, this body cannot move in a circle. Let this be very clear, because if I keep on writing, it will be too much of writing. I repeat once again. As long as the body is rotating, there is a centripetal force. So centripetal force is must. If the body is rotating with an acceleration or angular acceleration, there is a tangential force. So if in our case there is an angular acceleration because we have applied a force. We have applied a force. Centripetal force. This centripetal force, this centripetal force, whose value is equal to mv square by r, which we have seen in our chapter. This centripetal force passes it passes through the origin. Now, considering the force, if the centripetal force passes through the origin, of course, it does not contribute, passes through O. So, not contribute. Centripetal force does not contribute any rotational motion because if you also again want to find out the torque of this centripetal force, here let me write it. Torque force is zero because torque is the force vector multiplied by the position vector. Here, the force vector and position vector both lies on the same straight line. So angle between them is zero. So the cross product RF sine zero is zero. Clear? You should not have any confusion. Of course, if you have any misunderstanding or confusion, you can always write to me in your comment section. Does not contribute because torque of the centripetal force is zero. Let me also write, if you forget, since L between this tangential force which is mr alpha, this creates rotation. So we go back to this. We have seen that the centripetal force does not contribute in rotation, but tangential force, rotation. Tangential force contributes in rotation. If tangential force contributes in rotation, we should measure its torque. So torque of the tangential force, torque of the tangential force. What is the torque? We have earlier seen R multiplied by F. Here R and F are at perpendicular, so we can do their scalar product. Torque of the tangential force is the R into the tangential force is mr alpha. M alpha is equal to m r square alpha. So torque tau is equal to r square alpha. And alpha is the angular acceleration. So we discover a relation between the torque and angular acceleration, like there was a relation between the force and the linear acceleration F equal to ma. Where torque is equal to mr square alpha. So these two equations are, so this equation is very, very important, particularly if you go into engineering. This relation is very, very important. If we have F equal to ma, which is equal to this, mr square alpha. And mr square is designated by a new terminology, which is I, let us say I into alpha, where I is equal to square. So we arrive at a beautiful relation that torque T is equal to I alpha. This is analogous to F equal to ma. A was linear acceleration, alpha is angular acceleration. Is the force which produces the acceleration here. Torque is the force which produces the acceleration. And if you agree to replace the m with I, then the two equations are set. This factor or this parameter I, this parameter, this I is point of shear. A very, very important terminology if you go into engineering, moment of inertia. So here we find a relation. In linear motion, we had a relation F equal to ma. where we could measure the amount of force with the help of linear acceleration. Here, we can measure the torque with the help of angular acceleration if we know I. If we know I. Now, now we consider only one point. Now, if there are many such points, this lamina is made up of many such points P, Q, R, S, T, U, V, etc. And all cases, let us say all the points or elements that I have taken have the same mass m. They could have different mass m1, m2, m3, etc. Right? Distances are r1, r2, r3, etc., etc. Then the total torque, only the summation of this. So total torque, this technique we have used earlier, total torque, which is represented by the capital tau or capital gamma, is equal to only summation of all these small torques mr square alpha. And alpha is same for everybody because alpha is the angular acceleration. It has to be same for everybody. So this is equal to you take alpha outside, alpha sigma r square. That means equal to I alpha. So first we discussed or developed our equation on the base of one point P. Now we just add R, S, S, T, V, etc., 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 etc. So I is so for an extended object, for an extended object, extended object, I is equal to sigma m. I is equal to sigma mr square. That summation of all mr square taken together is the same sigma mr square. So what we finally find is that torque is analogous to force. This you need to remember. Torque is and mass and moment of of inertia is analogous to. If you remember this, and if you have properly learned your lessons of the linear motion, you will find you can very easily solve all the problems of circular motion or rotational motion also. Okay? Now, lesson we shall stop here. Next day's lesson, we shall do a little bit more on the various physical parameters and relations of your rotational motions.